Hello, am I audible?
Yes, ma'am.
Thanks. We will start with week 8 today. Okay, so for in week 1, we saw some basics of control systems. From week 2, week 3, we saw some mathematical tools like Laplace transforms and how to represent a system using transfer function that we saw. Around week 4, we have started time response analysis. And week 5, we saw one of the control technique or one of the analysis tool that is called Root Locus, which is a time domain based analysis tool. In week 6, we started off with frequency responses and we saw two plots. One is Bode analysis, another one is Nyquist analysis. Now, in week 8, we are going to revisit this time response base again, that is designing controllers using Root Locus. In week 9, we will revisit this. 9 would be designing same controllers using Bode. Right, so that's why we have made a basic understanding about these two techniques like Root Locus and Bode in the previous weeks. Now we know how to analyze a system using these two techniques. Now we are going to do one more step, that is building a controller to control the entire system, to make the system work like according to our wish, whatever design specifications we need. We are going to force the system to give that design specification by adding a controller. That controller we are going to design using these two techniques in the upcoming weeks. Now, this week is going to focus mostly on the root locus based techniques, that is time response based techniques. Now we need to recollect all those time response, those specifications like peak time, overshoot, settling time, what else? What are all the specifications we studied in the time domain specification week that we need to recollect. Then we need to recollect how we can design a root locus for a system. These two are the basic for this course. Right. The major question is, why are we doing this and what is the outcome we can expect out of this? In transient specifications, if we see like overshoot, peak time, and everything, it represents the system's short term behavior. So, all of a sudden, if I give some input, how my system's immediate behavior would look like. The next part, that is steady state, we already know how to split the system into two things, right? One is transient, another one is steady state. So this transient tells about the system's short term behavior, while the steady state tells about the system's long term behavior over a period of time where the system is going to settle. Is it settling or tracking the desired set point, or it has some deviation out of it? If so, how to reduce the deviation? And in transient response category, is it giving proper time response specifications like too much overshoot or very less settling time? This decides the response rate of the system. Is it very slower or is it very faster? Is it behaving accordingly to my wish, or it's behaving in some random way? So if it is behaving some random way, we need to tweak the system to make it behave in a desired way, right? So out of this, we have the most common two things that we are going to see in time domain specification is, one is overshoot, another one is settling time. So based on these two, or by controlling or changing the behavior of the system to accommodate to this characteristics. For example, I will say I need a 90% overshoot and zero point 0.5 second settling time. So I will first check what is the actual system's overshoot and settling time, and I'm going to introduce a controller so that the final system will give this 90% overshoot and 0.5 second settling time. That's how we are going to work on this in this week, right? Now, to explain these things, that you would have seen videos, so I don't want to repeat the same thing again, but I want to let you know visually how this changes, like what is dominant pole and how poles and zeros and stability affects the system based on the location of poles and zeros. For that, we will see some examples in the MATLAB. Now, hope my MATLAB screen is visible. If not, let me know. Okay, I have taken some different systems. For example, I have taken this transfer function. Let me run this and explain it side by side. So this is the transfer function. If you see, all the coefficients are positive, or if you see here, the poles are like s is equal to -3 and s is equal to -2. Here in this figure, I think this figure would have not been visible if I present like this. Okay. Yeah. Okay, now if I run again. Okay, now this is the entire representation of the system. So if you see, all the coefficients are positive, and this is the origin. 0 is here, and the poles, two poles, the system has two poles and no zeros. Two poles lies in the left half of the S-plane. One is lying around -2, another one is at -3. And I have made a unit step response. Like I have given unit step signal to this system and make a closed loop step response. So the step response looks something like this. So it is going to towards a set point, but I have simulated it over this point of time. Once you simulate, it will settle at some point. Okay, let me make a little bit changes that I'm going to add 1 0 to the system. Previously, there is no 0 here. Only 2 poles are there. I'm keeping the poles at the same location, but just adding a 0 to it. So this is the second response. If you compare these two, can you see the difference? Like it is taking a little bit slower response, but it seems to be little faster than the previous one. So your effect of 0, you can learn the behavior of effect, adding effect of 0 here, right? When you add a 0, your system behaves faster than the previous one. But the important point is here is it is stable 0, adding a 0 which is on the left half of the S plane. Okay, the first point is adding the 0 to any system will improvise the will make the system work faster. It will reduce the settling time, so the system tend to work faster, and it reduce overshoot also little bit, and it doesn't increase overshoot. That's actually the correct way to explain this. So here you can see addition of 0, and 0 and poles are the same location. Actually, there is a phenomenon happening here, that is pole 0 cancellation. Both are at same location. So the effect of 0 and the effect of pole will be cancelled here. But if I keep the 0 at some other place, you would see the faster like response as it is, as I said before. This response now is because of the only pole that is here. Okay. I'm going to make another change, that I'm going to bring the system to the one of the poles to the right half of the S plane. What do you expect? How this step response should be? Should be obviously unstable, right? So I hope everybody is with me. Any doubts so far, or anything is not clear, whatever I'm telling? Please respond. Are you all with me?
Yes, ma'am.
Okay. What about others? Gayatri, Aishwarya, Sayantan, Manoj.
Oh, yes, ma'am.
Okay. Okay. Aishwarya, Manoj.
Yes, ma'am, not doubt.
Okay, right. So stop me then and there if you have any doubt. Okay, I'm just pulling one of the poles to the right of the S plane now. You can see the one pole is here. That gives us a unstable response, right? One pole is in the left of. What if we pull both poles to the right of the S plane? That doesn't add much changes. It will again be a unstable response. Even with one pole at the right half of the S plane, 10 poles in the left of the S plane, the system is going to be unstable only. No pole should be at the right half of the X plane. That is the thing we need to follow. Right. Now, both poles are in the left half, but I'm going to pull the 0 to the right half. What do you expect? Will it affect the stability of the system? Can you type it in the chat box? Just adding a right half 0, will it affect the stability of the system? Will the system exhibits unstable behavior or no? You can say yes or no in the chat box. Will the system become unstable? Yes or no? Adding a right half 0 makes the system unstable. Yes. Kaushal said yes. Rest of the people? Manoj also yes. Okay. Gayatri doesn't know. Aishwarya Sayantan, what do you think of it? Aishwarya also yes. Sayantan? Yes. Okay. All of your answers goes towards yes. Let me check what it tells. If you see this, this is a weird behavior, but it is not unstable, right? So ultimately it is going to settle at some places. If I simulate for a more over time, it will settle at some around 0.25 or something, sorry, 0.37 or something, around it will get settled. So, keeping a right half zero doesn't affect stability, but this is an important notion that we call the system as a non-minimum phase system, where the poles, zeros of the system lies in the right half of the S-plane. It will add a phase lag that, for example, if the system original,
Ma'am, we're not able to see the figure, ma'am.
oh, why? I can see in my iPad. So let me,
That old figure only stays.
okay, okay, oh, yeah. I will present again. Is it visible now? A drop in the system?
Yes, ma'am. Yes, ma'am.
Ah, okay, okay, right. So, and the point I want to tell is adding a right half zero doesn't really make the system unstable, but it creates a additional phase lag inside the system. For example, if my original system's phase angle is 0 degree, it will add a lag that it makes a dip. If you plot the Bode plot for this system, you will see a dip in the phase of the system. There won't be any peak or any steady values of the phase. It will affect the phase of the system, not any magnitude or any other visible changes. So affecting the magnitudes, they can affect the stability of the system. So since it is only focusing on the phase, it doesn't really contribute to the stability, but it creates a delay. Physically, we can interpret this as a delay in the system. So if you have, for example, I'm waiting in a traffic, keeping my feet on a brake. I and all of a sudden, if I release my brake and put my feet on a accelerator and raise it to 50 kilometers per second, you will just feel that the car may go little bit backwards before going to the front, right? That is a kind of friction it is trying to restore. So that kind of thing is coming because of the right hand zero. It's a physical interpretation. We can say that delay or that dip, that phase lag, it's being given using this right hand zero. We call this kind of system as non-minimum phase system. You have to keep this thing in mind. Stability doesn't depend on zeros. Stability depends only on poles. Location of poles in the right half of the S-plane makes it unstable. If it is all the poles are in the left half of the S-plane, it is stable. If some of the poles are in the origin or in the imaginary axis, that we call the system is marginally stable. If two or more multiple poles are in the origin, then that can take the system from the marginally stable to the unstable region. So these are all the behaviors of the poles location based on. Right. Now, I hope you understood the zero doesn't contribute anything to the stability. That is the point of having this exercise. Right. Now, I kept everything to right off of this plane. Again, you see everything is unstable because origin is here, two poles, and one zero is in the right half. It is unstable because of the poles, not because of the zeros. Then I have a different system that has imaginary roots that lies in the, what is this, imaginary axis. Poles lies in the imaginary axis. The pole location is plus or minus 2y. So what is this kind of behavior? If you see closely, it's not like painted one, but it is a oscillation of constant frequency that ranges from
Ma'am,
1.2. Yeah.
again, figure is not there.
Oh, why it is not getting updated? Is it visible now?
No, ma'am.
Mm, I don't. I think the refresh rate is very slow. Okay, if I have both poles in the imaginary axis, so I have a response something like this. So it's not like a painted one, but it's having an oscillation of constant frequency throughout the timestamps. So if you see closely, it is a very minute changes in the oscillations. It's like a sine wave that ranges from -2 to zero point 0.1 based on the value of your pole and zeros location, and it is a constant frequency. It ranges from this extreme to that extreme every time in timestamps. So if you see, like, to see like this, it looks like very congested. Let me try to go into that. See, so it's not actually tinted, it's a oscillations of very minute frequencies. Okay, so if you have poles at the imaginary axis, you will get sustained oscillation. We call this as sustained oscillation because it is not going to fade or it is not going to increase anytime. It will sustain that frequency forever. Whatever simulation time you take, it will be at the same, oscillate at the same frequency. This is the example for an oscillator we used to keep in our watches or any real-time clocks. So these kind of systems we use in a that we need for a infinite time responses systems. Okay, now I am going to take another one example that has complex pair poles. I will share my screen again because it is not getting affected. Yeah, I hope it is visible now. So I have changed my poles from the imaginary axis and take it to left half of the S plane. Now you see there is a oscillation, but at some point of time, after some time, it is getting faded. So since these two are in the left half of the S plane, you exhibit a behavior that is not sustained oscillation but oscillatory in the initial stage, and later it gets faded and reaches to a steady state value. So this kind of systems are the underdamped systems. So that has a tau value that is in between 0 to 1. Okay. When that the previous example is a undamped system, there will not be any tau value. Tau would be 0 for that kind of system. Okay, these are all the examples we have. So is my screen visible now? Another code I have opened.
No.
No, okay. Okay, for some people it is visible. For Gayatri, it is not visible, I think. Okay, let me go for a second example, but observe this very closely. I'm going to simulate a system with different tau values, and I'm going to plot the step response for those systems. See, can you see the figure now? The pole keeps changing. See, I'm taking the pole from the imaginary axis towards the left. Its physical meaning is I'm changing the tau value. This is the current tau value. I'm changing it from 0 to now it's going around 0.3, 0.4. It goes around like this. So previously it started like this. Now it is getting a overshoot, and the overshoot is getting diminished as the tau value increases. So the poles goes towards the left half of the S plane further and further. So when it reaches left half of the S plane, almost the overshoot gets decreased, right? It's almost zero now. Now let us wait until it reaches the real axis and see what if both poles are at the same location. So it is going to approach that. See, now there is no overshoot, nothing. It's the ideal system. This is the critically damped version of that. Now this both of these two poles separate, goes away in the direction. Now one goes towards the left of the system, making the system stable and stable. The another coming towards the right. So this doesn't matter, but whatever poles that is near the imaginary axis, that is a dominating pole that influence the system much. So based on this influence, you are seeing there is a steady state error. The response keeps shifting and shifting. As it reaches the imaginary axis, ultimately it is going to be a unstable system. So once it crosses this imaginary axis, it has become extremely unstable. It goes to infinity. Now it becomes unstable, right? So we couldn't see this here because I have kept axis equal. So this is the different behavior of the system based on the pole's location that affects the stability of the system. So I will do once again. You see carefully from the beginning how it is going. See, okay. See, it was oscillatory. Now the oscillation is getting to fade as the poles goes towards the left half of the S plane. I keep increasing the tau value here. So now overshoot gets decreases, settling time is also improved, faster responses. So the famous line here says farther the pole, faster will be the response. So if you keep your poles farther from the imaginary axis to the left of, faster will be your response. Now one of the poles keep approaching the imaginary axis that includes the steady state error and making the system from stable to unstable. It is pulling towards the unstable region. So once it reaches the imaginary axis and starts to move ahead, it will completely become unstable. So your stability defines based on the poles and based on the tau value, your response specifications will vary. How much overshoot you need, how much settling time you need, how faster your system should be, or how slower you want it to be. You don't need any oscillations. Or minimum oscillation is okay, but ultimately I want a steady state value that is closest to my set point, like a low or zero steady state error. So this is how your design specifications will vary. So if the system doesn't really give the desired specification as it is, you are going to force the system by keeping one controller in the feedback or the feed forward path. That will make the system to design uh, behave in a desired way. Now we'll go back to week 8 content and see why do we see all these things. Here, we'll start off here and come back to the. So this is why we saw all these examples. Here you see dominant pole is there, no? So whatever poles that lies close to your imaginary axis, if it is here, so these poles dominate more than the poles that lies in this regions, any region. So the distance between these two poles should be at least 5 times. So if it is 1, the another pole is 5. So this will be considered as a dominating pole where it affects the system response more than the one that is in the left of farther, like that is the 5. S is equal to minus 5. Let me explain it clearly. So if you have two poles, let me take it as minus 1, it is minus 5. So if I change, I have a system behavior like this. For example, I have something. Okay, so if I change minus 5 to minus 6, there won't be any much changes here. It may be like this, maybe like this, but doesn't really make any further changes. But if I change this to maybe 0.5, then you see a very big changes here. So That's why I'm saying the poles that is near to the imaginary axis, that is called as a dominating pole, it slows down the system. So how near it is, that much it will slow down the system. So the farther the pole, faster will be the your response. Either way, you can keep that in mind. Closer the pole, slower will be your response. And the pole that is closer to imaginary axis will be the dominating pole, and that contributes to much to the response of your system. So tuning this pole location is very vital than tuning the -5 pole location. So if you want to change your system response, I have a 90% overshoot. Let's take this is my set point. Maybe this is zero point 0.9. So I have a 90% overshoot, and I want to bring this overshoot little bit down, that at least it should be 50%. So I need to touch the pole that is near to this, and I want to change this pole to left or right so that I will reduce this overshoot. For that, you need to know what are all the changes this tau affects if you want to increase the overshoot or decrease the overshoot. Okay, and why do we need controllers? I have been telling this for a long time, right? So I have a design specification. This is the design criteria, but my actual system, that is G of S, if I give some R of S and expect some C of S output, this doesn't behave in a way that it gives a design specification. So I am going to force the system by including a controller to this plant or my original system and take a feedback so that I know what is happening inside the system. By doing so, I will try to force the system to give this desired specification. That's why we need a additional system called controller that regulates the system behavior so that it behaves in a expected way. Not so good, not I cannot define it as good or bad, but in a expected way, in what way you need or what way you want the system to behave. In time domain specifications, that making this to work in a design specification can be done using these two characteristics or any specifications of the system. One is the peak overshoot, and second is the settling time. So out of peak time, rise time, or any other thing which there, peak rise, delay, out of all these things, why do we choose these two? Because as I said, you are close to whatever pole that is close to your system, that mimics the response of the system. So the response, peak overshoot and settling time is closely related to the pole location by this formula, minus zeta omega n plus or minus j omega n root of 1 minus zeta square. So based on your omega n and your zeta, you want to change the location of the poles so that I will get a desired specification. In the other way, I am going to change the location of the poles based on my design specification such that its overshoot should be this and its settling time should be this. If you are confused about this, I will write it here. So I have a system. I will explain it using an example. For example, I have a fan. So I am giving a 200 voltage and I'm expecting the fan to rotate at 1000 rpm. But the fan I bought is not giving 1000 rpm. It's only going up to 800 rpm for whatever reasons. I don't know. Some physical limitation is there inside the fan, so it is only going to 800 rpm. But the problem here is I cannot change the voltage. The wiring in my house is fixed. I cannot change the voltage rating. I cannot add any other step up transformer or anything to make the changes. It will be too tedious. So for this given voltage, I want to get the 1000 rpm somehow. What I'm going to do here is I'm going to keep the voltage same, but I'm going to add another person here known as regulator, where it has different resistance values inside it. So I can get to choose what resistance value my fan should rotate at if I want to get in a 1000 RPM. So first what I'm saying, I'm just introducing this and keeping this idle first. Okay, before doing this, I want to see, I should know, how do I know whether my fan is rotating at 1000 or not? For that, I need a sensor, right? So I am keeping a tachometer here. It measures the RPM. So I'm keeping a tachometer. This is a sensor, and this acts as a feedback. So it is telling the system that your fan is not rotating at 1000, it is rotating only at 800 RPM. This 800 RPM is getting inside, this 200 voltage is coming here. So this will be plus and this will be minus. Naturally, it is a unity feedback system. So now I know sensing part is over here. Sensing done. That I know just my fan is rotating only at 800 RPM. Then comes the controlling part to make this goes from 800 to 1000. Right? This is the next step I want to do. So for that, I'm hiring another person. Let us see, regulator, and this is the controller in our control system point of view. And I have my original system and I'm getting the same sensors or tachometer reading and giving it back to the system. Right. Now what this regulator will do, in regulator, we have 5 regulator usually at home we have, no, 0, 1, 2, 3, 4, for example, this 5. When you put in 0, it will turn off the fan. Ultimately, if your switch is even on, it will make the system like fan goes off because it has highest resistance. So the fan cannot rotate or the current cannot flow out of this resistance. Later, it will try to reduce the resistance as you keep on going the number. So 4 will be your highest number. So I am choosing a regulator that it has 3 as a 800 RPM. It has resistance that mimicking the 800 RPM. So if I want to go to 1000, I have to choose 4 as the final speed for my fan, right? Physically, you know this, but mathematically or in an unknown system, how will you know that if you have a manufacturer that doesn't disclose anything? That's how this compensator design or controller design has. This is what you did in the PID controller design. Or for PID controller, what you did, KP, KI, and KD you tune all these gains so that you will keep the location, or for example, if my fan is rotating at 800, my poles are at this location. That's why I'm getting a 800 RPM current. Sorry, speed. So this is my 1000 RPM, but my original system is only giving 800 RPM. There is a 200 RPM difference is there because my pole location is here. Maybe point is point. Randomly I'm choosing, okay? Just to explain this concept. So now I want to push this to here so that I will get, I don't care about overshoot. I am just very concerned about my final value, steady state value. Ultimately, it should settle at 1000 RPM, this red color I want. So I should know whether I should keep the system pole locations here or here. So these pairs I don't know, right? That's how you choose this KP, KI, KD so that you change the pole location to get the desired response. But in some cases, you say you saw that only P is not enough. Only changing the constant is not enough. So I went with PA. Sometimes it increases the overshoot a very large, but includes a steady state error. But reduces the steady state error. In transient responses, if I want to check, I went with PID control. In compensator design also, we are having 3 different types: lead, lag, and lead lag compensators. So here we are going to do the same thing, but in a different manner. I am going to ultimately change the whole location here also by designing my compensator. That is again a controller. Compensator and controller both are similar, but compensator is a more loosened form of controller. In controller, you only change the gains to look for the steady state. Here in compensator, you can work around transient, steady state, everything, zero location, pole location, you can do whatever you want. It's a more loosened form of, if you say it is compensator, I would say it is a controller. Right. How do we design this and what are all the different specifications of this lead lag compensators? That is the next question. So your compensator design will be common. If I say in many books there are many different representations. For example, some book follows one by say alpha, one by beta kind of. This is lag. This is lead. But I'm going to start off with a common representation, that is GC of S should be same, S plus Z, that is 0, divided by S plus P, that is pole. Where for a lead compensator, your Z should be less than P. This is for lead. If Z is greater than P, it is lag. That's it. If you have both in cascade, for example, S by Z S plus P into S plus Z by S plus P, where this Z1, Z2, let's take. Z1 is less than P and Z2 is greater than P2. Then this we call it as lead lag or lag lead compensator based on the position shift. That's it. Both are same. Since it is a cascade, it will, the performance or the behavior wise there will not be any change. Okay. If you need some time or you need something to revisit, let me know. I'll give you 1 or 2 minutes. Let me take this as a GC lead first. GC lead, if I say Z S plus C divided by S plus P, where for lead Z should be less than P, right? Let me keep this in one side. Lag, I'm going to keep this in another side. Okay. So, what really varies when compared these two compensators? So, if you if you learn both of these separately by adding or making it cascade, you will learn with lag lead also. There will not be any changes. Okay. For lead design, for lead compensator, your pole should come first and your zeros should come forward. For lag compensator, you have a zero first and then a pole. This is the difference between these two compensators. If you keep pole near to your origin, then it behaves as a lead compensator. If you keep zero of the system near to the origin, that when compared to the poles, then it behaves in a lag compensator version. These are all the two different things you can design based on your design specifications. This creates a positive lag. This creates a negative lag. Can you um, connect with this? Because last time we saw when we keep a zero in the right half of the S plane, it creates a lag in the system or a dip in the system, right? So as you keep moving further and further to right half of the S plane, you will experience this lag, phase lag in your system. Then this positive lag, we call it as phase lead. This we call it as phase lag. That's what we saw in the non-minimum phase. As you further increase your system and makes it goes to the right half of the S plane. Right. If you sorry, if you study this system in terms of root locus, for example, if I plot root locus to the system, sorry, let me put this way. I have a system, original system, plant, and I'm plotting a root locus for my plant. So adding a lead compensator or lead controller in front of this plant will pull the root locus to the left. For example, if my original system root locus maybe should look something like this, adding a compensator will pull it towards the left. This is compensated system. After adding a compensator, this is the original systems. Same thing if it is for lag, it will be sorry, it will push the root locus. I'm not speaking about stability. Compensated, original and compensated system. So it will pull your root locus towards right. What this pulling root locus left and right means? Why we are concerned about this? Because pulling it left makes it eh, faster. Pulling the root locus to right makes the system slower. So faster means settling time is less, lower means settling time is more. Overshoot can also be increased in faster system. Overshoot can be minimum in slower systems. So indirectly, you are playing around keeping your settling time and overshoot or pole location around these three. We are playing around, right? Where to keep the pole so that my settling time is like this, so that my overshoot is like this. That's how we mimic the desired responses of the system. Okay, so important point here is we most probably prefer lead compensator to work on the transient specifications. We prefer lag compensator to work on the steady state specifications. So based on this, let me ask you a question. Okay, I have two systems. System 1, system 2. For system 1, everything that is in blue, that is actual response. Everything is red is a set point, and green is the expected behavior of the system. Now, in both system 1 and system 2, the expected response is at the steady state value only. For example, this is 1, I guess. Okay. Both are at steady state value. But in system 1, the blue is not at a steady state. But in system 2, blue is at the steady state. But in both system, the transient responses varies from the actual response. Now, for system 1 to behave in a proper or ideal way, what compensator you would choose? For system 2, what compensator you would prefer? lag or lead, lag or lead. What should be the most preferable controllers for this system one and system? You have any answers? System one lag, system two lead. Okay. Rest of the people, everybody try to answer. And that's okay if it is wrong. We are here to learn. Chris, Kaushal, Raman, Gayatri, Sayantan, Aishwarya. What do you think? What happened? Agree with Manoj, okay? Rest. If you answer only, I will know how you're understanding this. Both lag. Okay, system one lag, system two lead. Okay. System one lag, system two lead. Good. Okay. Any other? Raman, are you there? Okay. Yeah. What do you prefer for system one lag lead, system two lag lead? Out of this, which compensator you would prefer? Lag, system one lag, system two lead. Okay, good. I hope everybody understood that and answering it. Hopefully, lag, system one lag, we go because there is a much change in the steady state specification because it is not settling properly. So, in order to correct the steady state behavior, we go with lag. We prefer lag mostly there. For system 2, we prefer lead because I want to slow down the system. I'll change the location and that's mostly depends on the transient specifications. So I would go with the transients. Good. So far you understood the concept, but recalling this will help you answer faster in your exams. Just keep in touch with this. See this 1 or 2 days once, and you will see like you will know by heart. If there is a issue with transient, I will just go with the lead. If there is a issue with steady state, I couldn't make the system attain the steady state. I will first design lag and see how well my steady state specification improves. And what else we need to cover today? Can we start with designing a compensator? Okay. First, we'll start off with one of the compensators, lead compensators. Then we can move towards the rest of the comp. Yeah. Later we will study the same design and compensator same Bode plot. More or less everything same. Here, whatever we do in time domain, like settling time overshoot, there we are going to do in phase margin, gain margin. That's it. Systems are same only. Okay. First, before going to the lead compensator or any compensator design, you should know what is dominant pole that we have done. You should have an idea about your tau omega n and how it is mimicking to transient specifications. For example, if I increase the tau, will my overshoot increase or decrease? If I change my omega n, will my overshoot or settling time decrease or increase? This kind of interrelationship you need to know that you can learn slowly, but you have some idea, I guess. The first thing is if I give a system, I'm starting with the system. First thing, the step one I will do is I will first plot root locus for this system. We call this as uncompensated uncompensated system. The original system, first, whatever is in the question, we call it as uncompensated system before introducing or designing a controller or compensator. First, I will plot the root locus for this. Then I will check. Second step. This is like an intermediate step, just baby steps. I'm just explaining everything in detail. Checking the specifications of a system. TS, MP percentage, PR, PP, PD, everything. I'll first check, and mostly I will check these two clearly, like closely. This two itself will give me an entire information. Now, our questions will be first, I should have told this. Our question should be I have a system X with some specifications that we don't say. Just I have a system X and I want maybe A percentage of overshoot and B seconds of settling time. This is how my question will be. Compensator design question will be. I have a system X that I don't say anything about actual system specifications. I have a system X. This is the known information, and I want the system to behave like this. This is the future reference. You are going to make the system behave like this. I'm damn sure your system won't have this A% overshoot and B% settling time, seconds of settling time. That's how you will be given with the system. So first you need to know where the actual system is, right? That's why we are doing these two steps. First, actually, you plot the root locus, then see what is the actual percentage of overshoot and actual seconds of the settling time in your uncompensated system. That is the first two step of your compensated design. The third step would be calculating the deficiency, or I could say the difference. Now see how the actual system is and how you want your desired system should be. This we are going to change. So now we are going to choose the pole location, that is 0, and the P, such that you will get this desired specification from this actual specifications. So your old Z and old P will be something. So I would have now I am taking a lead compensator. So I will take Z1 plus P1 where Z less than P. So I myself will get confused every time. Z less than P is lead, right? Okay. P into S plus Z old by S plus P old will give me my this entire thing will give me by A percentage of overshoot and B seconds of settling time. So this is the overall way you are going to calculate a lead or a lag compensator. Right. Now, can we design one? Maybe in MATLAB or by hand we can do. We take the question. Okay, I will take this problem. GC is just checking with only the dominant poles. Okay. Let us solve by hand, but the visuals you can see here. So I'm choosing this example as strictly DC. Consider a system X. This is our X, as I said before. Design a controller such that your closed loop system has. So I want this part of the I want part. So your ultimately your final you or should have a overshoot lesser than 16 percentage, should have a settling time lesser than 6 seconds. So the first step as it is, what you will do, first you will plot a root locus and examine the actual systems MP percentage and TS. So let us do that. You can solve it by hand. This step you already know, right? Just use the formula e power minus zeta pi divided by root of 1 minus zeta square. That's how you do by hand, right? E power minus zeta pi divided by 1 minus root of zeta square. Settling time would be 4 omega n for let's take it nothing given. So for these two, you will find it by hand, but for root locus and everything, in order to reduce the time, we'll do in MATLAB first. This my system is equal to transpose of this G1 is equal to 1 divided by S into S plus 2 into S plus 4. Okay. Now I'm plotting a root locus of this G1 and I'm seeing a step response of this system. It won't be possible. Okay, let us just zero focus. So this is equal. This is the root locus of my system, where my root locus pass through pole is around minus zero point 0.8. Actual poles are at 0, minus 2, and minus 4, where my root locus crosses my real axis by minus zero point 0.8 around. It's actually 0 imaginary axis. I have kept at different points. So there is no overshoot. If you see, overshoot is 0 percentage and damping is 0.99 percentage. Sorry, 0.99 zeta value. It is 0.9. So overshoot is actually 0. It should be less than 16 according to the design criteria. But we don't know like 0 is also okay, it is also lesser than 16 only, but we want to see the settling time also, we have to see both, right? So that can be done using finding the dominant pole location. So I will write here. Sub minus j omega n dot minus zeta square. So we know zeta is equal to 0.998 from the root locus we found, and omega n is also there. Frequency they have mentioned, um, zero point 0.8. It is around zero point 0.8. So if you find this, you will get this frequency, right? 0.9 into zero point 0.8, around 0.76 it will be. That's what given here. Yeah. So this minus zeta omega n plus or minus j omega n root of 1 minus zeta square will give you the dominant pole location, that is SD, which is that is the minus 0.667 plus or minus J1 1.15. From these two specifications, we got this zeta and omega n, and we found the dominant pole location. The idea behind this is you want the system to behave in a desired location so that you reallocate its poles, right? The indirectly you can say the actual or root locus of the actual system, if you redefine it to go through the dominant poles of your system instead of having a root locus here or somewhere else, if you redefine the root locus of the system or change the gain of the system so that your root locus pass through your dominant poles, then you will surely say it is attaining this desired specification or given specifications. So the idea to go to the desired specification is to relocate your root locus so that it pass through your dominant poles, because your dominant poles are built from the specification itself. So this is the overall idea. So if you want to shift the root locus, if your actual root locus is here but your pole location is here, you want to shift the root locus towards left, right? So which compensator will shift it towards left? Lead compensator. Sorry, lag this is original, right? Towards left, lead compensator will shift your root locus towards left so that your desired specification is met. So that's how we choose lead or lag, by analyzing the actual location of the system and finding where the dominant poles passes through. Okay, now we want to shift this to where is the actual pole. Actual pole is here, but your dominant pole is here. Your root locus here. You want to change it, shift it towards the left of the S plane. So you would design a lead compensator. Your lead compensator should look something like this: Z plus ZP, where Z is less than P. Now the motive is to find where is this Z, where is that P, so that I can design a proper compensator. So for that we have some formulas. It was not given here. Lead compensator. So if you want to design this, we have done this step already. So I'm in lead compensator, we are just redefining this into a actual pole are mimicking the concepts where z plus z by s plus p, where z less than p. So if my z is 1 by t, it should be 1 by t with some constant, so that it will be, this will be lesser than this, right? That's the idea. So if your z is 1 by t, your pole should be alpha into t, so that your z will be less than your pole. Sorry, 0 will be lesser than your poles. So any doubt here, why 1 by t above or 1 by alpha t below? Your lead compensator should look like this, where z should be less than p. If I choose z as 1 by t, that is in terms of time constant form, then my poles should have some constant, that is alpha, so that this will be greater than this. If I want this to make greater than this, then I would choose something above. So this will make it, or in the other way around, this will always be, if I choose this, I will choose pole as this. That's it. Just the inverse of this. Which one is lesser and which one is greater based on the compensator we choose. Okay, that's why the lead compensator design is like this. If you see lag compensator, you will get some idea. See, where beta is greater than 1. Same, if you use the same alpha, then it is okay. It would be 1 alpha by t then. But here, in order to change the system from one to another, we are just keeping this different variables, where here alpha is not, it will not be greater than 1. It will be from 0 to t. The alpha will be from 0 to 1. Whereas in for a compensator, sorry, lag compensator, this is the same 1 by t divided by s plus alpha t, where your alpha will be greater than 1. In order to differentiate these two, we are using alpha for lead and just beta for different variables for lag. But concept wise, both are in the same loop. Right. The formula to calculate we left it this step, right? If I want to design this controller, I want to know what is the Z location and P location. The first step is to identify the angle deficiency. We will talk in terms of both magnitude and angle. So the angle deficiency, if you want to calculate, this is the formula. For angle deficiency of ZC, this is a formula where it depends on this gamma will be contributed from this angle. It is between the origin and your compensator pole, where it is going to come with respect to your dominant pole location. Angle between your dominant pole location from the origin. That's what this gamma will give you. So if you put the pole zero diagram of this, if we want to do the root locus design, we will find the angle of departure, right? How the root locus will go. So for that, we will calculate the angle between each and every poles and the zeros. So one of the like dominant poles angle from the origin, that will give you the gamma. That's what we usually do for root locus. So while we design a root locus itself, this information you will get from that. Then, so this will give me the ZC and PC, the location of Z and the location of P. So that's how. Once you get this, you will just write the pole location 3.5, for example, randomly I'm writing, plus 2. So this will go into cascade form of your actual Z actual and this S plus P actual. Then to verify this, the last step is to design a root locus or plot the root locus for the compensated system. We call this as compensated system. And see the time response of those system, where your settling time and overshoot criteria has been satisfied. Both settling time should be less than 16. Sorry, what is that? Less than, how much is that? We saw in this example, right? cycling time should be here for this 6 seconds. So whether it is 6 seconds and the O should will be lesser than 16 percentage of that system. Similarly, you will follow the same step for the lag compensator. Just your representation of the system would be different. 1 by t divided by s plus 1 by beta t, where beta is greater than 1. For this, s plus 1 by t divided by s plus 1 by alpha t, where alpha lies between this. This is the difference between these two signals or a compensator. These are the compensators, it's at the closed loop pulse, value of the compensator. What is value of the compensator? Select step response. Sixteen point three percentage. Your price time should be 0.6046. And your Steady state error should be for a unit ramp. Should be equal to 0.0125. Okay. We'll design a compensator. We don't know whether we need lag, lead, or lead lag. So we'll just start with this problem and we will design one by one and check. And there is no constant value that's how you design a compensator. Whatever value that satisfies the overall performance, that is the actual compensator design. There is no straightaway method or a constant answer for this kind of problems. Okay, correct. In point two decimal places, you cannot tell how it is. So whatever compensated design you find that satisfies these three or these two, whatever specifications they give in the question, that is the correct answer. You just have to ethically prove that your compensated design has satisfied all this criteria. That's it. Right. First, we know overshoot we have given with the rise time instead of settling time in this question, and there is both transient check we have to do and steady state check we have to do from this question. First of all, if you find the actual steady state specification and transients of the system, and if you find one of this satisfies, then any one compensator is okay. If the steady state is satisfies, you would need only lead lead, right? For transient it is, yeah, you would only need lead. If the transient satisfies but only steady state means, so you need lag. But if both doesn't satisfy, then you need lead lag compensator, both cascade and compensator you need. First, we need to find the dominant pole location. At formula, we know SD is equal to minus zeta omega n plus or minus root of 1 minus zeta square. Now, how do we find zeta and omega n? From the specification that has been given for us. That we know MP overshoot is equal to e power zeta pi divided by root of 1 minus zeta square. We know this 16.3 e power minus zeta pi root of 1 minus zeta square. So we take log 16.3, sorry, long it is. How do you have this feature then? Yeah. What is ln of 16.3? Will be around it is in percentage, no? You have to find it in 0.163. It should be because 16.3 is in percentage. I would need in numbers. So divided by 100, it is 0.163. So this may give me 1.81 or 1.82. Zeta pi root of 1 minus zeta square. This will always go like this. Zeta pi. So if I want to get rid of this root, what I will do, 1.82 square minus zeta square equal to minus zeta square into pi square I will take. Where if I keep, what is pi square? Minus 4 into 9.85. 9.82 is 3.31. 9.85 minus zeta square minus zeta square equals 9.85 divided by 3.31. 2.97 minus zeta square equal to minus 2.97 zeta square and minus zeta square It's 2.97 to the square equal to 1. And we minus 1.97 to the square equal to 0. Of course, somewhere I made mistake. How it is 0? Till this point, it is correct. Pi by, it's correct. Pi square divided by 1 by zeta square is also correct. Let me keep this here itself. Write it 1.82. I let me put in the equation, find the one spending most time. Okay. So now we got, if you calculate this, you will get tau is equal to zero point 0.5. The next step is to find the omega n. So what we have, rise time we have, we used MP percentage that has only zeta. If I write the formula of rise time, it would give me 1 by omega n. That's why they gave rise time. Some omega n, rise time, what it is, 0.6 something, no? 0.60, 0.6 I am keeping. 1.8 by omega n is equal to 1 by 8 by 0.6. Plus around 2.9. I can say 3, maybe, okay. 2.9 is fine. 2.98. Okay. So this is my zeta equal to 0.5, omega n equal to 2.98. It's my answer. So my dominant pole location would be always dominant pole should
Ma'am,
occur in pole pairs. Yeah,
what's the rise time formula?
rise time formula 1.8 by omega n
Okay.
plus or minus root of 1 minus zeta square, where zeta 0.5 into 2.98 and 5 into 2.98 1.49 plus or minus root of 1 minus 0.5 square 0.25 is 0.75 3 by 4 root 3 by 2, right? So 1.732 divided by 2 means 1.03 something, 0.4 let's take. So it will be dominant pole locations will be some 1.49 plus or minus square root of 4, or it is right around 2.6 it will. Okay. So this is your, I'm just again approximating for ease of access. So this is my dominant pole location out of the specifications they give. So if my root locus, this will come near here. Maybe if this is 1, this is 1, maybe this is minus 1, let's I take. Maybe, uh, 1, 1, 1, 2, 2. So my location will be 2.6, 1.5, right? Somewhere here it will come. These are the two of my dominant pole location based on my specifications. I would have some root locus of my system. For us, maybe I am plotting my, if I plot a root locus for the uncompensated system, let's take it is here. I don't know where it is, but the idea is I want to shift wherever the actual root locus is. I want to shift it to go through this dominant location. Then my system will give all this or satisfies all this design specification. That's what the idea is. If my actual root locus is here, I would include a lag. If my actual root locus for my uncompensated system is here, I would, sorry, if it is here, I would include a lead. This is this will be lead, no? For this to pull towards left, it is lead. For this to pull towards the right, it is lag. So even if I put a lead, but if I couldn't satisfy the steady state behavior, then both I have to do, lead and lag I have to do. So for that we need to see the root locus first. First we need to plot the root locus. If I plot the root locus, I will just do quickly on MATLAB instead of doing all these steps. But in exams, you might need to do that. You need a lot of practice. I don't have that right now. Okay, what is the system? 10 by s into s plus 2 into s plus 8. Okay. 10 by s into s plus 2 into s plus 8. R locus of Q2. Yeah, so minus 2 I have one pole, minus 8 one pole, and 0 one pole. So this is my system. So if I want to do plot the root locus, actually it is passing through minus 0.93 somewhere. Zoom this. Minus 0.93 minus maybe around 1 meters. This is my breakaway point. This is breakaway point. Minus 1 and my root locus crosses the real axis at minus 0.035. Minus 4 minus plus 4. Plus 4j minus 4j. It is crossing like that. So this is my actual root locus. But where is my dominant pole lies? It lies in the minus somewhere here. Minus 1.5 and around 2.6. So this is my dominant pole location. Roughly I'm drawing minus 2.6j, 2.6j. So now I have to pull my root locus towards left. So what compensator I have to choose? Lead compensator I have to choose. How my lead compensator should be? S plus z by s plus p, where z is less than p. So it will be 1 by t divided by s plus 1 by alpha t, where alpha will range between the 1. So this is how my root locus, sorry, compensator rule look like. So if I let my root locus pass through my dominant pole location, then my transient response specifications will be satisfied. Then I have to check with the compensator system whether my steady state response is being satisfied. Otherwise, I have to design another lag compensator for that. So this is my overall idea behind this. How we are going to find the ZP, that is in the next step. Now we found the dominant pole location. So yeah, then we have to find the angle of deficiency as we saw in the presentation. So the angle of deficiency formula is it's given in the presentation, right? B2 something. We have to find the angle between each and every poles and the zeros that has been there. For example, it is minus 180 minus angles from origin to all the poles and the zeros. Oh, sorry, only poles we consider here for this. Origin to the poles. So it will be in our case minus 180 minus of angle from S. So the first pole is at S, my 2 and 8, right? So first pole is at minus ST at your dominant pole location. You have to substitute your dominant pole location in the actual pole you have in your system. Then it will be from dominant pole plus 2. This is your actual pole where S becomes your dominant pole location SD. It's not normal S, it's SD, that is dominant pole location minus SD plus 8. That's your another pole, right? Third pole. So from this, you want to calculate all the angle between these two. Now, what is your dominant pole location? SD is equal to minus 1.5 plus or minus 2 point something we got, no? 2.6 J. This is your dominant pole location. Now, we want to find minus of angle. It will come as it is. It will be tan inverse of, because that is the actual location. There is no phase or any compensation we have to be do here. 2.6 divided by 1.5 minus of tan inverse of 2.6 divided by, it is real poles, right? So minus 1.5 plus 2 minus tan inverse of 2.6 divided by minus 1.5 plus 8. Right? This you have to calculate. So this will roughly give me tan inverse of 2.6. Can you anyone find and tell me quickly tan inverse of 2.6 divided by 1.5 minus, so will be tan inverse of 2.6 divided by 1.5, that is minus 0.5 minus tan inverse of 2.6 by 6.5 overall minus 180 in terms of radians we have to find. So this will be, it will be infinity thing, that will be minus and minus. This will, so actually it won't be near to infinity. Larger value it will be. Then it is 90 degree. So overall should be around 60 to something. It is coming for me. If you have some different value, let me know. Okay, this is the angle of deficiency. You want to find your actual, like actual root locus is like this, but you have here. So this is the angle between these two, actual and your desired root locus from the overall transfer function, the dominant pole location. Right now we find the angle of deficiency. Now location of compensator 0 we want to find. before that, one step is there. This is the actual angle of deficiency, gamma, from from the pole where your next location should look like for the root locus. So for that, the formula will be 1 by 2, 180 minus theta minus z. Sorry, phi. You have to find. So theta, we know cos inverse of zeta, where zeta is zero point 0.5, we found zero point 0.5, right? Just, zero point 0.5 zeta is zero point 0.5. And this will give me cos inverse of 1 by 2, what it is? 60, right? So theta is also 60, pi is also 60. I'm just equating to 60 because it will be easy to calculate. Like 1 or 2 degrees, up to 5 degrees, it doesn't matter because that compensation we need to do for it anyway. So you can either keep it 62 also. There is nothing a problem. For ease of calculation, I'm doing it right now. 180 minus 60 minus 60. Otherwise, it will come in two seats and it will be difficult to do all these things. 60, 60, it will be only 60 by 2 with 30 degree. So gamma is here, 30. Right. The next thing is to find the zeros location of your lead compensator because we agreed our actual is here. I want to push it to left, so I want to find the lead compensator. So for that, the formula we saw in the presentation, right? What it is. We see if you see that also. So this choice of zeta we calculated right now. Now we want to use this formula omega n sine gamma divided by sine theta plus gamma. So your is a C location will be omega n sine gamma divided by sine of theta plus gamma. Everything you can find from the known information, right? So now omega n, you know where it is omega n, 2.98 around 2.98, and sine of gamma is 30, sine 30, 1 by root 3 or something you will get, right? Sine of theta is 60 plus gamma is again 160. Oh, sorry, gamma is 30. So 2.98 into 1 by root 3. Maybe I might do something wrong. Please let me know if you have any questions. So sine 90 is 1, sine 30 is 1 by root 3. 2 by 1 by root 3 is 1 point. It's hard to decide from here. It's around 3, let's take. 2.9 is, it is equivalent to 3, right? It's again coming under root 3 around. So your ZC would be around root 3, like approximately I'm doing. So omega n correct. By 8 by 0.6. Yeah, it is 3 only, no? It's correct. No, we found our zeros s plus z by s plus p's z we calculated, it is around root 3. It is coming. It's a sine root 3 once. Sine 1 divided by root, it is root 3. Point by 4, 0.54. Sorry. Sine 30 I have to degrees, sine 30. 0.5. Oh, for sake. That's why it's not 1 by root 3. It's 30. Sine 30 is 1 by 2, right? It will be 30, 45, 60, 90, 1, 1 by 2, 1 by root 2, root 3 by 2. This will be root 3 by 2, 1 by root 2, 1 by 2, 0. Right, okay. It's 1 by 2 actually. Correct. Sine cos degrees. Okay, so it is 1 by 2, then 3 by 2, sine 91, 3 by 2 it is 3 by 2 is around 1.5. So we found s plus z by s plus p, where z is 1.5 we found. Now the next only remaining step is to find the compensator pole location. That also we know formula. Just everything is formula. The idea is whether you will need to design a lead or lag compensator, that you have to do properly. Then rest of the things you can just follow the formulas. 30 plus 60 divided by the sine of theta is again over 60. 30 plus 60. 4 into sine of 90 divided by sine 120, 150 degree. I don't know what is 150. Sine 91, sine of 150 will check. Sine 150. 0.5 again. 2. Your PC is 2. Now your lead compensator is yes plus 1.5 by s plus 2. So your important point is your compensator should be stable. You should not design an unstable compensator and telling that I am getting this value only, and it will make the system unstable, right? If your poles are in the right half of the S-plane, then it will make the entire compensator system unstable. There is no point in controlling any unstable systems. So make sure your compensator design is at least stable. Let comes the pole location later. Okay, we design a lead compensator. Then the one thing we need to check is whether the lead compensator is enough, whether it is satisfying both transient and steady state characteristics. Okay, that we need to find. For that, we need to plot that. And in order to find the steady state error, we can just check whether the velocity error constant satisfies, because they have asked steady state error for a unit ramp, right? Where it is question. For a unit ramp step it is position error 1 by 1 plus kp. So E of SS is equal to 1 by 1 plus kp, where for ramp it will be 1 by kv, where your kv is limit s tends to 0 s into g of s. So you need to find the velocity error constant for unit ramp to find the steady state error for it. So we already designed one system. That's our this for example my g of s is this 1 divided by s into s plus 2 into s plus 8, where gc of s is equal to 1 divided by see, I made this stick. 4 by 0.5, is it 2? Is it 8, right? So this will be 8. So my compensator design is 1.5 divided by s plus 8. So your overall system should look something like this. 1 by s into s plus 2 into 1.5 into s plus 8 the whole square. So it increases the system to another 1 degree because of adding this pole, right? So just for gain change, I'm just considering k here also to find the gain value what my lead compensator will give. Some gain value I'm considering for now. Maybe around 1 I will consider for now. So with this, if you plot this, you will find the proper gain value. If you plot the root locus for this, and if I want to make the dominant pole location from the root locus, let me draw it again with the compensated system. Okay. So by varying your root locus to see where that it is crossing your dominant pole location, your gain value will be around 190 it is coming. So your overall system would be GC of S is equal to 190 divided by S into S plus 2 into S plus 8 the whole square plus 1.5. So this is your overall compensated system, lead compensator system. The only thing left is whether it is checking whether it is satisfying your steady state criteria. For that, we need to do the velocity error constant calculation. So KB we know limit S tends to 0, S into G of S. So here it is GC of S into G of S. So because both systems are there in the feed forward path, right? That's like 190 S plus 1.5 divided by S into S plus 2 into S plus 8 the whole square. 1 S and 1 S will get cancelled. If I put 0, 1.5 into 190 divided by 2 into 16. This will get cancelled. 0.5. Okay. 1.5 into will be 1.5 into 95. How much it is? 1.5 into 42 and 43 around by 16 I'm getting. So this will give me KB. In KB will be something around 3. I just rounded off everything, whatever I'm getting. Around 2.5 to 3 it will come. Any value between 2.5 to 3.2 will suffice. Okay, now, so this is my velocity error constant. So if I put 1 by kV, it will be 1 by 3.9 around 0.33 around is my steady state error. What is the design criteria on the question? Your steady state error should be equal to 0.01. So we have to reduce this. Only lead compensator won't be enough for this because we have around 0.33 steady state error. But your design criteria is 0.125, right? 0.125. So we need to reduce the steady state error. We need to do a lag compensator also where it is S plus P, Z is greater than P, where I can represent it in terms of this S plus 1 by beta T. Beta is greater than, sorry, 1. Beta is greater than that. We need to design a lag compensator also. How to design a lag compensator? Since we already designed the lead compensator, this is a little bit easy. We have a lag compensator that will be a mirror of this lead compensator such that combining this lead and lag alpha and B will be equal to 1. Overall, the gain should be 1. So you design some with the alpha. I want to design the rest of the beta for the lag compensator. So with this value of beta, your velocity error constant should be equal to the one that is given in the desired specification 0.0125. So how can you calculate this? Alpha is equal to ZC divided by PC, where your already compensated system has CC 1.5 divided by PC 8. This will give me 1.5 by 8, it is 0.18, 0.19 maybe equal to 2. So your alpha will be equal to 2. I'm taking, sorry, 0.19 means how can I approximate? It will be equal to zero point 0.2. That's it. Alpha is equal to zero point 0.2. So given that alpha equal to 0.2, alpha beta equal to 1, beta equal to alpha by 1 by alpha, beta equal to 1 by 0.2. This will give me 5, beta equal to 5. So your new velocity error constant will be beta into your old velocity error constant, because that's how you make this compensation, right? 0.33 to 0.015. So because you know the relation between alpha and beta, so you are taking this to equal to 1, alpha into beta equal to 1. So beta will be calculated here, and the velocity error constant corresponding to this beta will be equivalent to the beta into your old velocity error constants. So beta, 5 into old velocity error constant, what do you get? What do you get here? Around 3, 3 you got, right? Old. So it will be 3, it will be equal to 15. Your new velocity error constant is around 15. So we should find the error constant for this. So your steady state error would be desired specification is to design a such that the steady state error is 0.0125 from here. Where it is? From here, 0.0125. So based on your steady state error, the relation between steady state error and your KV would be 1 by, right? Always ESS is equal to 1 by KV. For new system, it is KV bar. So your KV bar should be 1 by 0.0125. Your KB bar is equal to around 80 you will get. So this is for your new lag compensator. This is the difference between that, but this is the actual velocity error constant you should get for your new lag compensators. So the formula connecting these two would be KV dash divided by KV, where your new, this one you have to consider 80 divided by 3. This will give me around 80 by 3, it is 26, around 27 I am getting. So this is your new beta for your lag compensator, where your lag compensator will look something like this, 1 by 27 T, where this T can be the same as the T in this lead compensator. What is that? S plus 2.5 by S plus 8 we found, right? So 1 by T is 2.5 here. S plus 2.5 divided by S plus 8 by 27. This is your new lag compensator. So we design lead lag compensator for this question, where your lead compensator is this divided by S plus 8, and your lag compensator is this S plus 1.5 divided by S plus 8 by 27. You can put this in MATLAB and easily verify. Your actual system is 1 divided by S into S plus 2 into S plus 8. Actually, this is a very big problem which has cascade compensator. This is your actual system or compensator system, I would say, which satisfies both transient characteristics and steady state characteristics. There is no other way. You can check this only on the MATLAB. Otherwise, you have to calculate root locus and all the steady state error for this new compensated system for this whole. So it will have around 1, 2, 3, 4, 5, fifth order. So it is like 5 order system. You cannot really calculate using your hands. So if you have any doubts, we can solve more problems like relation based problems and this kind of very mathematical, rigorous, step by step problems in upcoming weeks. If you have any doubt now, you can ask me, otherwise, we can wind up the session. Okay, wind up.
Thank you, ma'am. And
Thank you.
this week's 8th week's lecture slides haven't been uploaded.
Okay, okay. I will ask that point of contact person to upload. Thank you.
Yes, sir. Thanks. Along week 9 also
What?
week 9 also can be
Week 9.
included.
Okay. Okay, right, right. Done.